Hello, fellow humans. Hang on. Volume down. Volume down. What am I doing here? I don't know. You can probably hear that my voice sounds a bit strange. That's because I have been really sick for the last week. And I'm... Am I sweating? I don't know. It could be the antibiotics. Okay. Let's try to have some semblance of normality here. Normally abnormal. So, I acknowledge the traditional owners of this land, the Whadjuk Noongar peoples. I pay my respects to their elders, past and present, and to Aboriginal elders and people from other communities who may be taking part in this live stream today. I am really seriously mushy in the brain and just trying to hold it together. So we shall see how long I manage to survive today. I was at work last Monday and worked through Monday evening as usual, and then went home and started feeling bad Monday night, and I've been really sick since then. And just... Simon says caffeine makes mush go hard. I've got some iced coffee here. I already had one coffee. So, who is here? Who is here? Good morning to Simon, Crispian, Scott Miller, Michael Wise, Gerald42, Peter, Mitch is here. Some call it fun. Imi, I hope you're doing well. And Any Mules, The Lane, Matt, Jordan, David, Tech Nebulous, Stephen George, Austin. Austin, I am so glad you're here because I'm going to be asking you questions today. You are going to be my help desk. Mitchell R is here. Cassio, Stephen W. Did I say David Howes? I can't remember. But anyway, good morning, David. Right. And Amanda is here as well. Very cool. And Mike O'Connor, driving back from Forbes, currently between Keith and Taylor Bend. I have no idea where any of those places are. Where is Forbes? Where is Keith? Who is Keith? Keith? Keith Richards? I don't know. Which Keith? But somewhere between Keith and Taylor. Luminator, good morning. Near Parks. Okay. Crispian said it's near Parks. Parks, which is where the big radio dish is. The famous Parks. B-A-B, says Peter. Yes. Okay, Peter. You be back in a bit. The dish, that's the one. Yes, when Chris and I... when Chris and I went up to LinuxConf on the Gold Coast, we stopped at Parks and saw the dish. Now, what? My favourite version of the US National Anthem. Oh, and John Whips is here as well. The list keeps growing. Jax Tech. Good morning. Why is Keith? Yes, why is Keith? Alright, so... Okay. Me being sick this week has had a side effect. A potentially good side effect. This is one of the benefits of being too sick to do anything much. I haven't been able to... I basically hardly left my room for days and days, just feeling bad, not being able to sleep and that sort of thing. And Oh, Crispian says, I stayed overnight at the Dish and charged my car with their electricity with permission. That's right. So for those of you who don't know...
Mitchell R said, ha 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 ha, evil sounds.
Evil sounds, yeah. Crispian has a... Actually, I think you might have 2 volts. Is it a Volt that you have? And he drove one a lot of the distance around Australia to going on a big road trip in an electric car, an old electric car, which he's told part of that story at one of the barbecues. Holden Volt, Mum has one too, says Crispian. Yes, that's why I was saying you have 2. And technically, I think one of them belongs to your mum, but they're both yours now. John Whips. All right, so that's right. What I was saying was the side effect of being... Ooh. Okay. I got to address this before I get into this other thing, because the other topic is the thing that I'll be talking about for a while. Amanda just said, I finished the design and have printed the Rat Cat Retract, which is a Patchbox remake. I will send photos and video and print files next week. That is really cool. So last week, Amanda sent some photos of her Patchbox project, doing a 3D printed version of a Patchbox, which is a device that you use in rack mount installations to allow neat cabling between different devices in the rack. It's like a self-retracting Ethernet patch cable, and you use little cartridges and put in as many as you need, different types to suit your requirements. And yeah, they are pretty cool, but also pretty expensive. And having an open version that we can 3D print ourselves is a really interesting project. So Amanda, that is a very cool thing to be working on, and I want to see the outcome of this. Yeah, so what being in a state of delirium did to me was that I was sitting there trying to stay awake a fair bit of the time, and with my laptop intermittently. After the first couple of days, I just was not capable of doing anything, and then got my laptop out, and it allowed me to spend time sitting there thinking about Testomatic and the design, and thinking about changing the design based on some of the feedback that I've been getting from people on the stream. I should press this button to start launching Fusion so that it's ready when I want it, and incorporating some of those changes. Now, one of the important changes, one of the big changes, was moving away from using all of those separate little IDC cables to connect to the different I/O and to go to a single connector. And so the PCI connector was something that was suggested on the stream. I can't remember who suggested PCI, but there was a bit of discussion about it, and it was generally considered to... Michael said, clicks Fusion. Jeopardy music plays. Oh, the Fusion splash screen just opened. It took that long to open the splash screen. And this is on an M2. It's not like a super slow old computer. So there was some discussion about using something like a PCI connector and then making the module that plugs in use PCI. And I really like that idea. So as you can see, I bought some PCI connectors. I ordered a pack of them from LCSC, I think I got them from. They're pretty cheap, a couple of bucks each, I think. And they seem to be pretty decent. And also, one thing that I was worried about, no, I won't get into that right now. But anyway, it was just about the insertion involved in that. I will show you some things once I've got Fusion up and running. Yeah, so it allowed me to just start thinking about decoupling myself from what had been done before. One of the tricks when working on projects like this is to not become too wedded to what you've already done. And some people have trouble with this, some don't. Sometimes I do and sometimes I don't. Like, there are times where I have been bitten in the past through my professional career by tech debt. A situation where you have designed something or you've built something based on the information that you have to hand at the time. It's your first pass attempt at it, or maybe second pass attempt, or whatever. The best information you have, and the judgment calls that you make mean that you design something in a certain way that you think is going to satisfy those needs. And then you discover that in reality, there are problems. You need to change your design, make alterations to it. But there are certain things that can lock you in, and certain things that you can't change. And so the whole issue of tech debt or technology debt is when you have existing design elements that you can't change, or that are expensive to change, or they're broken but you can't go back and revisit them because you don't have the time or the budget or the resources.
Version 0.9.0 is never recognizably related to version 0.1.0.
Yeah, that's right. And Michael says, today's drinking game, take a shot every time John yawns. We're all doomed. Yes, you will be highly intoxicated or highly caffeinated by half past the hour, I would guess. Yeah, as some call it fun says, no problem as long as it's a shot of espresso.
Austin's_creation said, help desk is in place with their milkshake.
Very good, thanks Austin. So I'm going to be talking to you about USB hub stuff, and nothing too complicated. I'm just going to show you what I've done, and get the master to review my work and see if I'm on the right track, because Austin is the master when it comes to USB hubs, particularly smart hubs. And I'm not trying to do anything as complicated as Austin has done, but yes, anyway, we'll get to that. We will get to that. Where was I? Yes, tech debt. I had no idea that I was going to start talking about tech debt. It's just the way these things go. Right, okay, sorry, just checking the chat over there. So, it is very easy. I talked about this a few weeks ago. I can't remember, maybe a month ago, maybe 2 months ago. I've lost track of time. When I was relaying the story of someone on Twitter, I refuse to call it X, who was complaining about the offset on Arduino headers and how they should have just fixed it after the first batch of boards had been done. And the Arduino header offset is a classic example of tech debt. It's where a mistake was made early on, and Massimo nudged the header off the grid when he was doing the final tweaks to the design late at night, right before sending the files off for production. And so we ended up with Arduino headers that have this weird spacing at the top. It's never been changed, never been fixed. And that is a classic tech debt situation where once you have something in place, changing it has costs. It has costs in terms of rendering things obsolete that may rely on the way you've implemented something. So you implement something some way, and if other things rely on you having implemented it that
Richard
way...
R. said, technical debt. I have seen companies with 20Y of T debt in software lol.
Yep. Way more than 20 years. It can really dig itself in there, and if it's in at the architecture stage early on, it can be a real problem. So one of the tricks, or not a trick, one of the keys in engineering and product development is recognizing when to call it, when to make a decision about, we have done this, we've just ordered these boards and they have this particular connector on it, but we've realized that we've made a mistake, and if we have this odd spacing, it's going to haunt us for the next 5 years or 20 years, and we need to change it. Do we make the tough call and change it now and invalidate all the boards that we've just made? Or do we put it off, and then the cost of changing it becomes higher and higher the further you go in and the more ingrained it becomes? Yeah. Yes. Austin says, heck, I was always surprised with the overall size. It was just large enough to be outside of the cheap PCB size that fab houses offered back then. Yeah, that's right. Yes. Anyway, I'm not going to get too much into the whole origin story of the Arduino. Yeah, there are a lot of stories about the early days of that. So, now, tech debt, that's right. Anyway, because I've got the first version of the tester, and it has now, we've been using it for flashing boards. How many has it done? I could look up the test records. I have test records, so yeah, just off the top of my head, it'd be in the order of a few hundred boards, I think, is when yeah. And so being in a mentally discombobulated state during the week meant that I kind of went off on this whole track of let's just write off the Testomatic and or Testomator as I was originally calling it, and consider that to be an experiment and not hold to anything that was in that design. So basically everything is up for grabs. Basic decisions like, should it be run on a Raspberry Pi? Should it use a Raspberry Pi Pico for the I/O expander? And I've gone through all of these sorts of things and the justifications for them. We have spent significant time on this stream getting the software working so that we could use Fermata to talk to the Raspberry Pi Pico and then control its I/O pins.
Welcome to the rabbit hole, John.
Yes. And the way we connect to the modules, should it be done with this? The screen that I've used on the Raspberry Pi, should it be the same screen? How should things mount to each other? Yes, Jordan says, "Ooh, breaking changes everywhere." That's right. And so I kind of went a little bit overboard. And when you look at it from the just at a very rough overview, you may not think that it's all that radically different, but there are many, many changes. The way this came about is my first plan was a minor incremental change. I'm just opening up this stuff now so I can show you.
Mitchell R. said, "A bit is just the right amount, haha."
Yeah. So my original idea was to make an incremental change. Now, this is what one of the tester breakouts looks like at the moment. This is a breakout for one of my clients, and their board mounts in here, pushes down on the pogo pins, and it can be programmed through this. Which reminds me, we also need to come up with names for the major components of this. And then it's got the IDC connectors along the front here, which connect to the chassis. I don't have the chassis out here on the bench. You've seen that before anyway. And I'm going to show you pictures of changes and things anyway. So this is where it started. as I was sitting there in a fever with my laptop, I thought, I know what I'll do. I will just make a little adapter. In fact, I wonder if I've got it here. TM mod archive. I started with, oh, I do. Cool. I will show you how I started with this. And this is not with anything in the right spot yet, but this is the general concept. And it's kind of upside down, and yeah. I began with this modification and then didn't follow through on it, which is why nothing is really in the right places and stuff is upside down and that sort of thing. So the idea was that I would take the original, actually, let's open this up as well. This will help with the, oh, in fact, what I could do, yeah, so the idea was, this is the existing Testomatic, or Testomator as it was called then. This is exactly what is running in the current prototype system. It sits horizontally like this in the bottom of the enclosure, and then IDC cables run from here to the adapter that is used by the specific for the device under test. And so my plan was, now I'm going to stick, oh, I can't insert it into the current design. Okay, let's do it this way. I'm going to go that, insert into current design. I'm just going to stick a couple of these things in here so I can, yeah, that'll do. Don't care that much about the position. And then I'll stick this into the current design. I'm just going to do a quick assembly so you can see where everything goes. Move it that way, rotate it 90 degrees that way. Oh yeah, the origins kind of make sense. Oops, nope, that. And move it there and move it sort of like that. Yeah, give or take. Approximately like that. Somewhere like that. Now imagine that this PCB was shorter. So if we go into, it wouldn't actually stick up that high. I hadn't done the dimensions properly yet. But this was the idea. This is the front of the tester on this side. So we have the control board sitting in the bottom, and then we have a riser that comes up here. And you can see that the IDC connectors here match the IDC connectors there. And then the, it's part of the adapter family. Ooh, yeah, we've got to come up with funny names for them. The board with the pogo pins in is part of the adapter family. She is called Anna. An adapter. Yes, Mrs. Adapter. So what I would do is attach this vertically inside the chassis and then run IDC cables from the existing control board onto this riser card, and then those adapters would plug in horizontally into this PCI connector. Part A, Part B, Part C, broken part. Yeah, and this would have been the absolute minimal change necessary to convert over to using just wondering about showing you something. All right, I'm going to take this off screen because I'm going to go into a different folder. I'm going to go into a client folder and open one thing. And this, yes, okay. Actually, it's all right to show you this because I'm in a test specific folder. It's not showing you all of the other client stuff. This is just for the breakout. Okay, so this is a modified version of the breakout that I started doing to experiment with the PCI connector on the bottom of it. Now this is an updated version of exactly this breakout. So this breakout right here with the IDC connectors across the bottom becomes this. It just has the IDC connectors deleted and it's got the PCI connector right on the bottom, and then it would just need routing to bring the signals to this header instead of to the IDC headers. And so that is that combined with no, not that, with this riser card would be the minimal change required to start using this connector. And that was my plan. That was how it all started. How it started, how it's going. We need the two pictures. So I'll get rid of these for now. We don't need those open anymore. This'll do. Then let's come back to here. Let's come back to here and just so that I can not dox myself with all of the client directories and things. Back to here, back into Testomatic, and now we can do it. So which one? Let's open that. This will show some of the changes. Open, open, open. Yeah, so that's what I started with. All right, so I was going to do this very simple thing, and I thought, you know, a couple of hours, I'll have this adapter board done, the new riser board. Where was it? Where'd it go? Oh. No, it's, I've run out of, there we go. I ran out of tabs. Yeah, I'll have the riser board done. We can iterate. There'll be a new version of the Testomatic. It'll all be fine. And then I thought, what if I moved a little bit of the power management onto the riser board? Because there is a very big limitation. This is a huge limitation that I discovered once I started trying to use the Testomator for real projects. And this is where the ideas that I have in my head start to meet reality, and I discover that I didn't really understand the workflow or the use case well enough, and I need to change my assumptions. So you can see there is this relay, and you can see these three, what are they? Sorry, 16 or whatever, parts that are here. These are current sensors. They are INA 260 current sensors, and this relay is to control one of the power rails going to the target device. And if we look at the, no, let's go back to the original Testomatic. You will see that I did not think through the power issues very well at all with the original Testomatic. So this is the relay. You can see the three current sensors here. And what I've got is the main power that comes in, which comes through this switch. I'll go through a fuse, through the switch, and through a diode, so it's polarity protected. And then it goes into here through to the main current sensor. From there it goes to the relay, and the relay switches it to the target device. So this is essentially just passing unregulated power from whatever the power source is, so nominally 12 volts or whatever, through to the target device. Also going to the target is a 5 volt rail and a 3.3 volt rail. And they are also being power monitored, and one of them is coming off this switch mode regulator. So we've got the little switch mode 5 volt regulator there. One of them is coming off this little 3.3 volt regulator. So we've got two voltage regulators on here. And that means that we have 3 power rails going to the device that we're going to be testing. Main unregulated power, 5 volts regulated, and 3.3 volts regulated. And only the main power is switched. Now, what this means is if the target device is being powered off 5 volts or 3.3 volts, we can't power cycle it. And it's one of those things that probably crossed my mind early in the design process, and then I never really followed up on it and thought of the implications of how much of a limitation this would be. And so I was at the stage of doing the riser card and that one. No, not that one. Yes, this one. I was at the stage of doing the riser card and thinking, ooh, I could improve this, because if I'm passing power from here and I've got the, so there's V in, 3.3 volts and 5 volts. I'm passing it through to the riser card here, and then from the riser it goes up to the PCI slot. That gives me an opportunity to control that power. What I could do is put a couple of relays on this riser board, and then I would have control over the 5 volt and the 3.3 volt rails. And it would give me that feature that I overlooked adding in the original design. And so that was basically the step that diverted me radically. The moment that I started thinking about, hey, how about I add some smarts to this riser so that it's no longer just a simple mapping of I've got IDC pins and I'm mapping them to PCI pins, and the riser begins to be something itself. It opens up all sorts of possibilities. Hang on a second. Oh, oh boy. Sorry, little coughing fit. And now my eyes are running. Actually, I've got to get a tissue. All right, muting again. And back. Yes, Crispian says, Jono dying quietly. Dying very quietly. Jordan asked, couldn't you just use FETs for power control? Potentially. Okay, so this is actually a very interesting rabbit hole. I'm not going to go into it too much, but this starts to get into an issue of high side versus low side switching. So if we are going to control power, then if we use low side switching, which means switching on the ground side, we can do that with an N MOSFET, but then we can't control the individual power rails. We could only isolate ground to the device under test. And that's potentially very dangerous, particularly if we are supplying multiple power rails, because there'll still be a voltage differential between those power rails if we take ground away. So the alternative is to use P MOSFETs and then switch it on the high side. So that can be done as well, yes. The issue with that is you then need a MOSFET driver. I mean, none of these are insurmountable problems. I'm just sort of laying out the issues here. So to turn on a P MOSFET that might be switching, say, 24 volts from a microcontroller running at 3.3 volts, you can't turn it on by driving 3.3 volts. Well, which way around is it? You can't turn it on or off, basically, because you do not have the voltage swing relative to the source. Anyway, my brain is not working well enough to be able to conceptualize this right now. the short version is, ideally what you need is something like a high-side MOSFET driver. And I've done this before. You can get a driver chip that you can drive with a logic level input from a microcontroller, which then connects to the MOSFET and allows you to turn it on and off, even if the MOSFET is switching a voltage a lot higher than the microcontroller can deliver. So pretty straightforward, not a real problem. We can put a PMOSFET on there and a MOSFET driver, no problem. So then there is a small voltage drop through the MOSFETs. I don't know, the more I'm thinking about this, the more I might change to using MOSFETs, but I'll show you what I've got so far, and we can see. Oh, Scott says, I do PCB testing in my day job. We always use mechanical relays or SSRs in our machines. Ooh, Scott. We have an expert in the chat. This is awesome. Okay. Yeah, I know they're really old tech, and they're slow, and they're noisy, but my inclination with this sort of thing is to use mechanical relays because you get close to zero voltage drop. They don't care about polarity or it's basically just like it's kind of a stronger way of doing it. I don't know. I can't word right now. Words elude me. It's just there is a higher level of isolation. If you are switching a relay, you have actual air gap between the control signal and what you are controlling. Oh, Scott says, read relays everywhere. Yeah. Yeah, read relays for things like open collector outputs. It just gives you total isolation, and if you screw up a connection and connect it backwards, it doesn't matter. All sorts of benefits to it. So yeah, in this situation, I kind of lean towards using mechanical relays, electromechanical relays, instead of MOSFETs. But anyway, this is just the way it is at the moment. Crispian says, using relays involves milliseconds where voltages can spike either way depending on latency. Yeah, that's right. I was actually measuring this only a couple of weeks ago. One of my commercial projects involves pulsing things at a known rate using relays. So I put an oscilloscope on a relay and I was running 100 millisecond pulses. So I was turning it on 100 milliseconds and then off for 100 milliseconds. But it was on the timing was based on just like the millisecond counter in the microcontroller. And what I discovered is that the relay will turn on within a couple of milliseconds. They are actually, I was amazed at how fast they are. Now, these weren't big relays. These were fairly small relays. They would turn on within a couple of milliseconds, but then they would take about 20 to 22 milliseconds to turn off. So from the moment that you turn off the power to the relay coil, it takes like 20-ish milliseconds for the electromagnetic field to collapse and the spring to start moving the contact away from the relay. So Jackstack just said, relays are fast makers, slow breakers. Yes, exactly. That's what I was seeing on the scope. So what happened was that I was driving the relays with a square wave with a 50% duty cycle, 100 millisecond pulse length. So 100 milliseconds on, 100 milliseconds off. And what was actually happening was the relay would be on for about 120 milliseconds and then off for 80 milliseconds. On for 120, off for 80. Oh, sorry, I should have muted before doing that. Oh yes, Mitch just pointed out the something that I overlooked mentioning earlier. Mitch said you don't need a gate driver to switch high side with a P channel, but P channel MOSFETs don't carry current as well as N channels. You can use an N channel on the high side if you have a gate driver. Ah, right, okay. Yeah, so the point is P channel MOSFETs, because of the way the chemistry works in the gate inside the MOSFET, have a higher voltage drop than an N channel MOSFET. I am nowhere near smart enough to understand why that is the case. I just know that that's the case. At least smart people tell me that that's the case, and I believe them. So yeah, P MOSFETs tend to have a higher voltage drop. So you can use an N channel on the high side if you have a gate driver. Okay, that is... maybe that was the circumstance in which I used it. I'm trying to think back to the project where I was doing high side switching. It was a couple of years ago, and I can't even remember which client it was for. There was some project I did, and I can't remember if I was using P or N MOSFETs on the high side. Anyway, my brain is not up to that sort of consideration right now. Scott said, commercial test equipment is basically large relay banks connected to measurement hardware. Yep. Crispian said, how long does a typical circuit board relay last doing that? Yeah, I assume you mean talking about the 100 millisecond cycle. So it was clicking 5 times a second, because it was 100 milliseconds on, 100 milliseconds off, which means it's 200 milliseconds per cycle, so 5 times per second. Jackstack said, about a year of continuous galloping in my experience. Really depends on how much current they are passing. Yeah. Okay. All right. My point here, I think I had a point somewhere. Let's see. Sorry, I just got distracted by a message. I have a client that's messaged me a couple of times this morning. Brain exploded. Okay, that's right. So I started off in my haze of sickness thinking...
Michael Wise said, Google's Ostentatus Australiana.
What? I don't get that. Sorry. Brain is totally faded. I'm having trouble thinking. Yeah, so once I broke away from making this just an adapter board and putting power control on it, things just kept going. So my initial step was to take this. The reason that this is in this state is I then duplicated this board. I wanted to just preserve this as I had got to this point, this riser board, and continue with a thought experiment. So I made a duplicate of the board, like duplicate of the whole project, and then just started doing modifications to it in an experiment to see how it would turn out. And then I didn't stop. I just kept changing and changing and changing. I began by adding some power control on the riser, and then I figured, well, I've got power control. I need some way of passing digital signals through from here to control those relays. And
Mitchell R. said, seems like TTS is also breaking long. He asked, there was a point.
Oh, okay. I didn't understand. So then I moved some other stuff up onto the riser, and I just kept going. And at a certain point, I started to think, why do I even have this bottom board? Can I just fit everything on the riser? So I did. Well, I'm in the process of doing that. And this is where things are getting to. Let's come back to... let's open this one as well. And then I renamed it from TM Riser to Testomatic 2.0 and moved everything around. Hang on, I'm going to change the camera method because it does Fusion does a stupid thing. See all these little jittery, goldy sort of colored things that appear? There's a weird rendering bug in Fusion when it's in perspective mode. But if I put it in orthographic, the rendering bug goes away. Okay, so what I started off with was putting a couple of relays on here to control power, and then I decided to add a few more things. So I added some breakouts. So these are MCP 23017s for the I/O control, because I thought I would make a radical change and ditch the Pi Pico. After all of that work, which was still interesting, and I think it was still worthwhile, it's a good thing to have in the toolkit, all of that work to get Fermata running on the Pico, I decided that I didn't need it. And that, so part of this came about when I started trying to implement real tests and going through the whole process of oh yeah, TechNebula said, just remember the edge connector power capabilities, especially at 10 amps. Yes. Where is it? Not that one. That's the old one. In fact, let's get rid of that. We'll clear up a few things here. Where's the... Oh, here we go. Okay. So, yeah, I'll show you header decisions and all of those sorts of things later. So you can see I've got a whole bunch of connections all doubled up. So lots of grounds. The main V-in has got 7 connections, a couple of connections to 5 volts, a couple of connections to 3.3 volts. I think the spec, someone's probably going to look this up and tell me I'm wrong, but from memory, I think the spec says that you can pass something like 1 amp per pin on a PCI connector. Now, you wouldn't want to pass 120 something amps through it because there are 124 pins, but you can pass a reasonable amount of current through. Now, I'm not intending to be passing 10 amps through this. That 10 amp thing is just for like a fuse rating. Blinkin' fits and sparkles. Michael says, we had a numbskull at work plug 16 amps of load into a PDU with the 10 amp plug into a 20 amp power socket. Yeah. Now, power. Okay. Decisions about power. That is a whole other rabbit hole. But for now, where are we? That one. No, not that one. Too many tabs. Is it this one? Yes. Okay. Let me explain. Okay, so thinking this through, the whole reason for putting the Pico on there was that I wanted to be able to run the tests on the Pico and have the Raspberry Pi just be like the user interface and the overall management system, but not for the Pi to be executing the tests. like driving I/O and reading signals and all of that sort of thing. My plan was the tests would be run by the Pico. The Pi would do something like load the code onto the Pico and tell it to run the tests and then get the results back from it. And that was the original idea. And then when Fermata came into the picture, which essentially takes the I/O that's on the remote device and exposes it to you locally, that meant that the code started to be run directly on the Pi and just using the Pico as an I/O expander. Sorry, my brain just fizzed again because that last message was about a client saying he wants to come over. And I'm having trouble keeping everything straight in my head. So what was I thinking about? I don't know what I was talking about. What was I doing? Wasn't it also so the Pico could be sacrificial? Yes, that's right, Jordan. So the Pico could be sacrificial because they're about $6. And so if the I/O got burned on the Pico, then I could unplug the Pico, replace it, and the Pi, which is like $100, is not damaged. So so there were some benefits to having the Pico on there. But then once the Raspberry Pi is the thing that is actually running the test, that's where the logic is, such as if we send this signal to the target board, do we get this output as a result? Or if we send it this command over a serial interface, then does it do this thing? And once I started trying to implement some of these tests, it became more complicated than necessary because of that split between having some code in the Pico and some code in the Pi. Even if the code that's in the Pico is just Fermata and it doesn't have to be changed on a per case basis, there are situations where we want to do things like and this came about because I began implementing test firmware for a client board that would be loaded onto the board to run the tests and then replaced with release firmware. And the test firmware that I started writing has a serial interface. So what would happen is that when the Pi wanted to run a test, it would load this firmware onto the target board, onto the client's board, and then would communicate with it over a serial interface and send it commands, and then use the pogo pins to measure whether it was doing what it had been asked to. And then, Jordan had a very interesting idea. I'll get to that. So it became unnecessarily complicated because I was already doing logic within the Pi. Because the question is, where does that serial interface go? And in most cases, it's going to be something like a USB interface. We need an actual USB connection to the target. What is going to be the USB host? The Raspberry Pi Pico can't be the USB host. Well, maybe it can, but that would be unnecessary work. So we need a USB host connection that can open a serial connection through to the target board. And it makes sense to do that from the Raspberry Pi. So at a certain point, the Pico just becomes irrelevant. And so I took it off. Now, Jordan just pointed out, seems like making a daughter board with the MCP 017s on them to swap out if they fry. That is a very interesting idea. I hadn't actually thought of that. I had thought through the whole thing of rework. Now, this board is not a cheap throwaway board. There is a lot on it. And some of these parts are moderately expensive, like the INA 260s. and yeah, the USB hub and all of that sort of thing. Like, I wouldn't want to just dispose of one of these boards because one I/O pin got burned on one of the on one of these I/O expanders. If that was the case, I would want to replace the chip and bring this whole board back into service. So maintainability on this is a consideration. And so by using I/O expanders and external ADCs and an external DAC, it means that the I/O of the Pi can be entirely isolated from the tester. So in theory, it shouldn't be possible to blow up the Pi from whatever board is being tested. Cable tie! Welcome and thanks for coming along. Now, I'm going to explain a little bit more about my power strategy here. Not that one, that is the Testomatic. This is it. Okay, power strategy. Power strategy, where
Mitchell R said, Opti isolators on the adapter board in the in-out way you want to do it.
Power in. Okay. Ignore everything else for now. I am just going to start by exploring my power strategy and the way I'm thinking about this. So we've got main power here coming in from this XT60 connector, coming in through a 10 amp fuse with a couple of bulk caps on it. This gives us our raw power in. Now, this will basically be coming from a lab supply or something. Like, what I'll do is have a lab supply sitting on the Alexa, stop. I don't know why I woke that up. So sitting up next to it, which is what I currently do. I've got a lab supply running the Testomatic V1.0. So this will give us our 12 volts or whatever coming in. Then we need several distinct power domains. And that main power coming in goes into the tester 5 volt regulator. So you can see here I've got an LMR3 8020 on here. So I've got a 2 amp switch mode regulator, which is providing us with a 5 volt rail for the tester. So this voltage regulator here is for powering things on the tester itself, including the Raspberry Pi. And you can see there is a Pi header here with 5 volt pins. So we are bringing power in, regulating it to 5 volts, sending it to the Pi. All well and good. The Pi has its own onboard 3.3 volt regulator. That provides us back 3.3 volts. Now, we don't have a huge amount of current we can draw from that, but we don't really need to. It's only used for a few logic level things. Well, yeah, I've considered making another 3.3 volt regulator, but anyway, let's just ignore that for now. So the current strategy is we generate 5 volts, send it to the Pi gives us a 3.3 volt rail in exchange, plus a bunch of I/O. Then the other power domain, so we've got power LEDs here. This is for the main V in. We've got the 5 volts, which is the rail that we are generating, and we've got the 3.3 volts that's coming back from the Pi. So we can see the 3 power rails there that are on the tester. Main unregulated power, the 5 volts we're regulating, and the 3.3 volts. It shows us the status of those. Okay, so that is for the power domain that is on the tester itself. It's for its own circuitry that it uses for its own purposes. It's not for the device under test. Okay, this sheet is related to stuff that's for the device under test. So here we have the main power coming in, and yes, I know this looks weird with all this white space, but this is just because I was trying to lay this out in a very modular way. So we've got the main power that comes in from the external power supply. and it goes in through a current sensor. The output of the current sensor comes to a relay, and the relay then controls power going to the device under test. And that gives us the ability to use the relay to power up the target device directly from the external supply, essentially, but through current sensing. So we can detect short circuits and things, excessive current usage. And this also gives us a way to very accurately measure the input voltage, because INA260s, they report the current, but they also report the voltage to a fairly high degree of accuracy. So it gives us voltage that we are supplying to the target, and there is an LED that shows us when target power is on, and that's on I2C. So then we have the second logical block in this. We have a second 5-volt 2-amp switch mode regulator. So there are two of them.
Scott Miller said, next step, design your own version of the Pi right on that board.
Maybe. No, I don't want to go that far. So then we are generating, once again from the raw voltage input, we are generating another 5-volt rail. This is not the 5-volt rail that runs the tester. This is a 5-volt rail dedicated to supplying the target board. Once again, it runs through a current sensor, and then the output of the current sensor goes to the relay, and then from the relay through a 1-amp polyfuse, and then from there to the device under test. So that gives us our switched 5-volt rail going to the target with current sensing and voltage sensing. And you can see I don't have an actual I/O assigned to controlling that yet. This is all a work in progress. Okay, so then we do the same thing, but for 3.3 volts. So we take the 5 volts that we just generated and we regulate it to 3.3 volts, which gives us a 3.3 volt rail. And again, this 3.3 volt rail is never used on the tester. This is only sent to the device under test. And same as before, I'm just repeating myself now, you get the picture. Current sensor, relay, fuse, blah, blah, blah. Okay, so what this sheet in the schematic gives us is three power rails going to the device under test, and all of those power rails are running through current sensors, and they are all individually switched by relays. So we can choose to power it up on any of those voltages. Now, one thing that I would really, really like, this is a future improvement. You can see here that I am generating a 5 volt rail and a 3.3 volt rail explicitly. But what happens if you want two 5 volt rails? What happens if you want a 2.8 volt rail? What happens if you want, whatever, a 7.4 volt rail? Because you're going to be simulating a battery or something. There are all sorts of other variations. So what would be really nice would be if each of these modules was essentially a programmable lab power supply. So we could, with its own current limiting and voltage settings and all of those sorts of things. So imagine if each of these blocks, like this block right here, for example, which is currently a 5 volt power supply with current sensing and a polyfuse, but it doesn't have programmable current limiting, it doesn't have programmable voltage settings, it's just a basic 5 volt power supply. Imagine if that block was a full programmable lab power supply that could be configured by the test profile. So the test profile could say, we need a 5 volt rail for this target board. So it sets the output to 5 volts and applies a certain current limit. And Some Call It Fun said op amp plus 15, minus 15, etc. Yeah, Oh, Andrew said, or just do that extra power logic on the adapter board until you decide it is a general enough need to put it on the main board. Yes, so that's right. There is this whole question of how much do you push down to the tester breakout that is specific to the target board, and how much of it do we bring back onto the main tester chassis
Cable
because
Tie
it's
said,
generalized.
"Oh, I like your thinking, John."
Thanks, Cable Tie. Yeah, so I'm trying to think of this in a modular way and not put things on here. This is the classic trade-off of we could build all sorts of things into the tester, but it may not be not everything is going to be needed by every target board, and target boards are going to have their own specific quirks. We need to be able to cover unusual situations. I will get to that. But yes, we could put, if you needed, say, a 7.4 volt supply, what you would do is take the V in, and on the breakout board for that particular DUT, you would put a 7.4 volt regulator on it and power it off the main V in, so that the actual tester breakout would have its own onboard regulator. So you can't account for everything. We can only do what we can. We've got to make that judgment call about how much do we build into the tester chassis versus how much do we push off to the breakout. And this is where I have currently landed, is an unregulated, like a raw VN, a 5 volt rail and a 3.3 volt rail. But my dream is for each one of those to be a fully programmable power supply. Okay, so now you've seen that. Not there. Not there. Where? Testomatic. Okay, this is it. So that this will now start to make sense. You see these three things here? These three things are those different power domains. And these are kind of like each one of these is like a module, but it's built onto the main PCB. We've got the two 5 volt regulators here. One of these 5 volt regulators is for the tester. The other one is for the device under test. Here we have a 3.3 volt regulator, which is for the device under test. We have another, oh yeah, and then we've got the 3 relays. We've got the polyfuses up here. And on this side, you can see that we've got these power indicators. So these are on the outputs of the relays. So if, for example, we turned on the 5 volt rail to the device under test, the 5 volt LED would turn on. So what this little row of LEDs shows us is what power are we currently supplying to the device under test. Then Cable Tie says one of these things is not like the others. Yeah, these two are switch mode regulators. This is a little 3.3 volt LDO. So we'd only get about 600 milliamps out of this one. We get up to 2 amps out of these ones. I could go for another switch mode regulator here, and that might be a sensible thing to do. But for now, I've just used a basic LDO. Okay, so the right-hand side, this whole area here, this, in fact, up to the divider, you see that where the little key is on that connector, that little key right there, that is the divider. That right-hand side of the connector is all power related. So this whole right side of the board, that part of the board right there that I've highlighted, that is all the power domain, like the power related stuff, confined to that section of the PCB. Now I do have main power coming in over this side, and I just had to do that for space reasons. So what I did was make a footprint where I can take a regular XT60 connector, like the connector that normally goes onto cables, and PCB mount it. And so main power comes in here. There's the fuse Here are the 2 bolt caps that are just on the input side. And then you can see an enormous track running along the top of the PCB there. That's the main V-in. That's the main fused V-in that then goes to the various voltage regulators and current sensor, etc. Alright, so, and up in the top left, you can see similarly the indicators on the tester power. So normally all 3 of these will be lit up. If everything is working, all 3 of these will be lit up all the time, because we have main power coming in, we've got the 5 volts that we are generating to supply the Raspberry Pi, and we've got the 3.3 volts coming from the Raspberry Pi. So all 3 of those should be on all the time. These ones will turn on and off as the device under test is being tested and power cycled.
Said, nifty XT60 idea. I wonder how mechanically robust it will be.
Yeah, that's a very good question, Cable Tie. So Cable Tie's question is about this connector and how robust it will be when attached to the PCB. I think the answer to that is extremely. The this, in fact, this is the one I was using to take the measurements. This is an XT60 connector, and I was using this to figure out the geometry. I have drawings for an XT60 connector as well, and I was just verifying that things really are what the drawings say they are, because trust but verify. And the size of the connections on this connector, these are huge. Hang on, what's the diameter on that? 4.26, it's reading 4.3. I think I can't remember what size I made the holes. I think it was 4.5 or 4.4. Yeah, 4.4. Where are we? I'm just backing it off a little bit. 4.4. Yeah, that has a little bit of leeway on it. Yeah, so they're going to, it's 2 very big holes with a lot of solder.
For what it's worth, I would guess. Pretty darn good. Yes, I agree.
Yeah, and this is only going to be plugged in and unplugged when the device is assembled. This is not something that's going to be plugged and unplugged regularly. It's an internal cable, and I'll show you a little bit about how that is going to work in the assembly in a second. Now, oh yes, and you can see a Raspberry Pi header there. I will get to that in a minute once I start showing you the assembly. There is a thought process behind that. You also see a weird notch on the left here. There is a reason for that, and you can see an IR camera connector, an external button connector. These are level shifters. So what I've got here is a couple of MCP 23017s, and I'm using one of them fully, and I'm only using half of the other one. So I could use a 23008 in its place, but I figured that rather than having 2, or I could have used 3 MCP 23008s, but oh well, it is what it is. I figured I would use 2 23017s. I've got 8 spare outputs on one of them, or inputs, which I could use in future for other purposes. So I figured I would just use that. Oh, Don said stick a silicon block under the base for support, under the board for support. Yeah. So that's for plugging this cable in and out. I'm really not fussed about that. And in fact, what could end up happening is just not populating this header, and I could just solder flying leads into these holes. That may well be how this ends up being made. But having a socket on it just gives more flexibility. All right, so just in passing,
said, 8 spare outputs now. Not so much by version 1.0.0.
Yeah. So the external button, this was because of something that I heard about on a podcast. It might have been on the Ohm podcast. I can't remember. Some podcast talking about testers and how it was someone who built something and they used a foot switch. Yeah, I have a feeling it was the Ohm podcast. And it was the idea of using a foot switch to trigger a tester. So you put the board on, you tap something with your foot and it runs the test. It's not something that I want to do, but I've got spare I/O, so I thought, what the hell? I will just put an external button header on the PCB. I may never use it, but at least the option is there. And if other people want to do that sort of thing, they want some external trigger, then go for it. No harm having it. So there's an external button. There's an IR camera header with a serial interface on it. That is a whole rabbit hole. That is a major rabbit hole, but I'm going to skip over that for now, and we might get back to that. Then there's a piezo just to make it go beep. These are level shifters on the I2C line and on the I2C bus.
Austin_creation said, don't foot switches normally use a 3.5mm audio jack?
Yes, exactly. So the thing is that this board, so I was thinking of putting a 3.5mm jack on the PCB. The problem is this board is going to be inside the enclosure. And so my new design strategy is not to bring any of these connectors directly from the PCB to the outside world. The only one is going to be the PCI header. Everything else will be leads going to panel mount connectors and things elsewhere. So what would happen is that this is a JST-XH connector, I think it is. So there would be a lead that goes from the JST-XH connector to a panel mount 3.5mm socket on the back of the enclosure or wherever it happens to be. And this is to allow different enclosures to be made to suit the geometry of whatever needs to be tested as well. Because I'm thinking ahead that this may end up being used by other people. The more I work on this, the more generally useful it seems. And people might want to make a different type of chassis and mount the button differently. They might want to mount the button directly on the box so that it's like a press button on the box. Or it might be an external button with a cable that you plug in. Like, I don't know. So by bringing it just to a connector here, it means that we can plug in whatever extra things we want to. Do it in whatever way we want.
Scott Miller said, external connections should always be separate from the main PCB if possible. Stuff breaks.
Yeah, that's a good point, Scott. On FranLab. Ah, yes. David T says, I remember seeing the foot switch and hand switch on FranLab a while back. That may well be where I heard of the idea. So Fran makes different types of devices like guitar effects pedals and things, I think. So yeah. Right. Then I've got a couple of ADCs. So these give me, are they 12-bit, 14-bit? I can't remember. Anyway, there are a couple of 4-channel ADCs, and there is a 4-channel DAC so that we can generate analog outputs. These are these ones here.
Said you might want a third pin for connection detect on the foot switch.
Connection detect on the foot switch. Maybe. These are all running at 5 volts. So these are level shifters for the I2C bus. And there are multiple I2C buses. I will get to that as well. I'm going to get to the connector in a minute because the way the pinout is set up is actually significant and it dictates a whole lot of this stuff. So, or at least it helps explain a lot of this. The Raspberry Pi's the Raspberry Pi I/O is at 3.3 volts. So we have a Raspberry Pi I2C at 3.3 volts connecting to these level shifters that come to the DAC and the ADCs, which are running at 5 volts. The reason for that is that it means that we can generate 0 to 5 volt signals using the DAC, and we can read from 0 to 5 volt signals using the ADCs. If I was running those chips at 3.3 volts, I would have a smaller range. And I wanted the 0 to 5 volt range on those devices. So with the ADCs, for example, if you wanted to measure more than 5 volts, then you could use a voltage divider. Okay, that's a whole extra design decision as well. because you might remember that on the original version, because I want to be able to read up to 32 volts. And so what I did was on the ADCs on the original version, I had a voltage divider on every input to give me the range up to 32 volts. But the thing is that, and that's because I want to be able to test the outputs of motor drivers, like read the motor driver output. And then I realized that what this was doing was taking a constraint, it was taking a requirement of a specific target board and dictating a design decision on the controller that didn't need to be there. And that is because my original thought process was that the adapter board for the device under test should only be a breakout. It should never have active electronics on it. I have totally rethought that decision. So instead, what I did was I've dropped the voltage dividers from the ADCs, and I've got the ADC inputs connected directly to the breakout. And then the breakout, if it needs a range beyond 5 volts, it can implement its own voltage divider or whatever methodology it needs. The thing is that in most situations, we're going to be doing things like measuring a 3.3 volt voltage rail to see if it's within spec, or measuring something like that. We just want to measure some signal, typically low voltage. And so putting a voltage divider in front of the ADC when we don't need it reduces our, it reduces our resolution, and it also adds bias to the signal that we are measuring. And I wanted to avoid biasing things unnecessarily. So anyway, I made the decision, I dropped the voltage dividers, and I'm exposing the ADCs directly to the target board. So that's the reasoning behind that. And then the MCP 23017s are running at 3.3 volts. So they are 3.3 volt I/O. Now this is a design decision that I'm still not entirely comfortable with, but let's skip over that for now. Now right in the middle here, USB hub. This is a TUSB 2046, which is the 4-port version of the hub that I used on the OpenKO, and it is the one that Austin used on his Smart Hub project. So we've got a single USB port here. I've got a vertical USB-C connector coming off the board. This is the input side of the hub. So what would happen is a cable would go from the Raspberry Pi to this USB-C connector, which then goes into the hub, and then out of the hub we have 4 USB ports. So those are the downstream ports. Those 4 ports will then come up to the riser so that they're available to the breakout. And there is a significant thought process behind that as well. Crispian said, does this circuit conform to normal PCI protocols? And the short answer is not even close. Some Call It Fun said, native PCIe pinout, any idea why each I/O pin is paired with its own ground in the socket? Is that a factor for your board? Well, that is probably a good segue. Answering that question is probably a good segue to looking at the pinout of this connector, because I think I've covered the major components that are on this board now. And where are we? Not that one, this one. This one. All right, now this header here, excuse me, this is the PCI header, which is going to the device under test. And I have gone to some trouble to annotate this because this is going to become the reference that you need every single time you implement a breakout to connect into this. You need to know what you're connecting to. And I've tried to group everything. So, starting from the top, even though it's mounted horizontally, this first part coming up to the key, so this, this chunk of the header right here is, I've lost it. let's get rid of that. We don't need that anymore. Don't save. Is this part up here on the right. So this is all the power related stuff. So what I've got is paired up power and ground pins. I've got all of the power pins on the top of the PCB. This left side, the B side, is the top side. The A side is the bottom side. That's the solder side. And this is the switched unregulated power going in, going through 7 pins with its matched ground pins on the other side. Then we've got the 5 volts going to 2 pins and the 3.3 volts going to 2 pins. So this gives us our power control going to the target board. And not all boards need all things. The majority of boards are probably going to need either just DUT V in or just 5 volts. Some may need different combinations. And cartridge connector, not PCI connector. Okay, hang on. Text-to-speech will say Scott's thing in a moment, which is a very good point.
Scott Miller said, card edge connector, not PCI connector.
Yes, that is a good point. That is a what's the term? It's a pedantic differentiation, but it is important. Yes, this is not PCI. I am using the same connector as PCI, but this is not PCI. So it is a card edge connector. It's just that most people know of them as PCI connectors. Yeah, so like if you think about the typical board, the thing that you're going to want to test, like this board, for example, which is one of my clients' boards, that's what that big breakout was for. I only want to supply the V into it because it's got its own onboard regulator. It's got its own onboard 5 volt regulator. It's got its own onboard 3.3 volt regulator. So I'm not going to be supplying 5 volts to it or 3.3 volts to it. I am only ever going to supply
Scott Miller
12
said,
volts.
pedantry prevents perplexity.
Yes, thanks, Scott. So in this case, what I would do when testing this is only turn on the relay for V in, and then what I would do is on the breakout, I would have ADC inputs that are reading the 5 volt and 3.3 volt rails to make sure that they come up and they are at the correct voltage.
Jack's Tech said, he is not the PCI H is a very naughty card edge.
A very naughty card edge. Yeah, so power. And you can see that I've labeled the major blocks of the connector. Now we also have here 5 volt and 3.3 volt rails. These are not the same as these ones. These are the tester's 5 volt and 3.3 volt rails. And that is for us to run active electronics on the breakout board. Like if we need to put parts on the breakout board, then we need power for it. And you'll see that there are also ground connections sprinkled all the way through here. There are many, many ground connections. All right, so the first major section is the breakout power and its I/O. So this is not stuff that goes to the device under test. This is all things related to electronics on the tester breakout. So the EEPROM, for example, which is on the breakout, that tells us what we've got installed. So that this allows us to the tester to identify what breakout has been plugged in. That the I2C connection for that is here. Then there is another I2C connection. So there are 2 I2C buses coming from the Pi. One is used for the EEPROM, the other is used for the general I/O. So this is the same bus as used for the I/O expanders and things. So what you could do is, if you ran out of I/O and you wanted more, you could always put an I/O expander on the breakout itself, because I2C is brought up here. You can talk to it and do whatever you want. Then we have the 4 USB ports in pairs. So we've got USB 1, 2, 3, and 4, and we've got D plus and D minus. These are coming from the USB hub. And the reason for that is that we might want to put something like a USB to serial converter on the breakout to talk to a serial port on the target board. Or we might want to put an ESP flasher on there. Or we might want to put a UPDI programmer on there. There could be all sorts of things. Originally I was thinking of building an ESP flasher and a USB to, and put serial ports on and put a UPDI programmer and all of these things on the Testomatic. And I realized I couldn't cover all of the possibilities. What if you need 2 ESP flashes? So the simplest thing is bring up the 4 USB ports, and then those things can be on the test breakout. So that's the reasoning behind that. And then I've also brought up SPI from the Raspberry Pi. So we got MOSI, MISO, clock, and then chip enable 0 and 1, plus a couple of spare other random IOs, and I need to assign one to this as well. This is so that we can do things like put a CAN controller on the breakout. If you wanted to be able to communicate with the target board via CAN bus, put a CAN controller on the device under test breakout, and we can talk to it over SPI. Or maybe, it could be anything. There are all sorts of things that you might want to put. So by having SPI and I2C brought up onto the test breakout, that gives us it basically is future proofing against things I haven't even thought of yet. Things that I want to build onto the tester breakout. It gives me the capability of covering that in future without having to reassign pins on the header. So yeah, I like that change. I think this will give a lot of future-proof ability. Scott says, passing USB through instead also means you're not locked into ESP. Yes, exactly. All right, so first major part, power for the device under test. Second major part, power for the breakout and digital like I/O for the breakout to control stuff on it. Now is when we get down into the actual connections to the device under test, and it's broken down into 3 main sections. There is digital I/O. So this is connections from the MCP 23017 I/O expanders. Oh, actually I need to get rid of those. I added that. I can get rid of these no connect markers now. That's I put no connect markers on different pins, and I had them on just about every pin to start with, and then as I connected things I removed the markers so I know which ones I've assigned. So for example, this I/O pin here I haven't assigned yet. It's just got net 38. It's not connected to any I/O on the Raspberry Pi, so it's got a no connect marker on it. So I know to come back and fix that. Alright, so we've got 24 digital I/O pins running through that I/O expander. So these can be either inputs or outputs. Pretty straightforward. Now that's 3.3 volt digital I/O. I'm still undecided about whether I should make that 5 volt, but I think 3.3 volt is the correct decision there. Then we've got, because the thing is that if I made it 5 volts, what I would have to do is for any target device that has 3.3 volt I/O, I would need a voltage divider or something on the output. So it'd be annoying. The common use case is 3.3 volts, so that's what I've gone for. And in a situation where you need something different, what you could do is put an I/O expander directly on the breakout, power it off 5 volts, run it off I2C, and you're done. So that problem is solvable. Then we've got analog inputs, and these are the ADCs, and you can see that I've only populated the first 8 because I've got 2 4-channel ADCs so far, and this is like a future thing. I'm probably going to do the first version with only the first 8 channels populated. I don't know yet. So these are 0 to 5 volt analog inputs running into those ADCs. And then these ones have not yet been assigned. And then 0 to 5 volt analog outputs coming from the DAC. Once again, I've got 16 channels assigned in terms of pins, but only the first 4 channels are populated because I've got one 4-channel DAC on the board going to the first 4 channels. So with this grouping, and yeah, I'd like feedback on whether people think I'm doing the right thing with this, whether this approach is correct. So I've changed this a fair bit actually, based on my original idea has changed a fair bit based on feedback that I got in Discord. I've rearranged some pins and changed orders of things and stuff. So anyway, I'm kind of happy with this. I think this makes quite logical sense, having these 5 major groupings on the connector and each one of them having its own specific purpose. It's quite logical. I like it. Yeah. Scott says 3v3 IO is most common now. Can always add level shifters to the breakout. Yes, exactly. And Crispian said, so it's future-proof with regard to channel expansion. Yes. Stephen W said, DAC, ADC, and digital I/O could be on a daughter card, so it's replaceable if you blow it up. Yep. So that was mentioned earlier as well, and that is a very good point. So what have we got here? I'm just going to... oh yeah, we've got Raspberry Pi header here, which I will get back to in a moment. External button, power LEDs, thermal camera. I've got my to-do list here turned sideways. Power. So this is the I/O. We've got 2 MCP 23017s giving us 24 channels of 3.3 volt digital I/O, because I've only got 24 channels brought up on pins on the riser. So the last bank of 8 on the second chip is being wasted at the moment. Could be used for something in future if necessary. Then our analog inputs are using these ADS 1115 ADCs. I can't remember if they're 12-bit or 14-bit. Hang on, I need to cough again. Oh, not feeling good at all. All right, so we've got the VSense inputs, and so tired. Oh, Mitch said, love the idea of port expanders on the I2C bus as a way of handling design time anxiety about not having the right pins on the card edge connector. Yep. Yeah, that's right. I can cover myself in future. Because now because I'm going to come back to that sheet in a second, but just to reinforce this point I was talking about earlier, if ever there was a situation where tech debt could come back to bite me, this pin assignment is it. Like, once I am fully committed to this card edge connector and the pins and everything on it, if I ever have to change this in future, and I have existing testers, I have existing breakouts, etc., then I would have to change a bunch of places. I do not ever want to change the pin out on this connector. So this is locking me in to like indefinitely, and this is setting the future of how this is going to work. So that's why I really put thought into making sure, by bringing this section up in particular, I am covered for the future. It means that even if other pins on the connector aren't so relevant, by having SPI, I2C, USB, and power coming to the breakout, anything just about anything you can think about that needs to be done that we haven't thought of yet can be
Scott
implemented
Miller
on the
said,
breakout.
Add a second card edge footprint in line with that one for expansion.
Second card edge footprint. No, that would make it huge. And I think this covers it by putting the by allowing us to build things directly. So if, for example, we wanted PCA 9685 LED drivers on the breakout to generate PWM signals, you could do that and then just connect them on I2C and you're done. So there are all sorts of things that you might want to do in future, or a different type of DAC to generate a specific signal, or whatever, a type of programmer like a high voltage programmer or something. It should be possible to connect anything you want because we've got controllable power and we've got all of this. Now, one argument could be that you don't actually need the rest of this connector. Like all of this part of it could be done on the breakout. And but the thing is that you generally need digital I/O, you need analog inputs, and you need some analog outputs. And so by covering those, this is going to cover, probably, like I'm just making up statistics once again, but it'll cover the vast majority of the use cases with no active electronics on the breakout board, which is the goal. We don't want to have to put things on the breakout board. But if you do need to put things on the breakout board, you can. And so this is where I need to be absolutely sure of the decision in relation to this pinout, because once I'm committed to this connector, then I am committed, and I'm going to try to stay consistent with that into the indefinite future. Scott says, don't recall seeing a reset signal line. Ah, that's a very good point. I did actually think about that, and I figured that I could use one of these GPIOs for that purpose. So these are not reset, not reset in terms of like Raspberry Pi reset or anything, but the Raspberry Pi can control these IOs, and if you needed a reset...
Said, what's the reason for so many grounds in the top small section? Might it be an idea to leave some unused, undefined for the future?
Yep, so cable tie. The reasoning for that is that these are essentially the return grounds that match these supply pins. And I wanted to just make them matched pairs. So if we're supplying power in on here, we've got 7 positive side pins, then we've got 7 matching ground side pins. So there are as many ground pins here as there are supply side pins to give us symmetry on current capacity. And yes, I'm aware that we have far more ground pins than supply pins because we've got all of these other ones. But these are, I interspersed these through the main blocks of I/O because these are basically the ground return pins for all of the IOs.
Said, okay, fair enough.
Yep. Scott says, I like to have a dedicated reset available that's not necessarily controlled through the controlling system, but can be if needed. This is an interesting point. Maybe that's what this pin needs to be. All right, Scott, tell me more. Tell me more. I'm going to add a note in here. Reset. So we've got SPI, we've got the 2 dedicated chip enable pins coming from the Pi. I've got 2 more GPIOs because I figured that I could use those as chip enables or something as well. And I was going to add another one on here, and Crispian said, what was the term used earlier regarding locking in the plan? I was talking about technical debt earlier, but that's like technical debt is normally a bad thing. Like it's used in the context of the term technical debt is that it's a bad thing, that you can't change something or you can't fix something or it costs you to fix something. So this is Yeah, it's kind of not really technical debt. It's a design decision. It's a conscious design decision. So, Scott says, ever had to do the button dance to program an MCU board? Annoying. Yes, that's right. Yeah, okay, I'm going to have a think about that, unless someone has a plan, because I'm not thinking clearly right now. But in terms of doing the button dance, that is what these digital IOs are for as well. And so if, for example, you were trying to program an ESP where you need to assert the GPIO 0 to put it into bootloader mode, on your breakout you would just connect one of these IO pins to GPIO 0 on the target. You would connect another one to the reset pin, and then from the Raspberry Pi we can now control boot mode and reset on the target device. And we could, if we had multiple MCUs on the target, then we can just use more pins. So we've got all of these pins under our control. But I get your point about reset being a dedicated pin at the tester level. For example, and also this brings up the issue of hot swapping. This is not something that I had ever thought about originally, but when Austin suggested using one of those little TCA hot swap I2C drivers, it really made me think that it could be an interesting idea. It'd be nice to be able to have the tester chassis running and pop out one of the adapters, pop in a new one, and you're ready to go with testing a different type of board without having to shut the whole thing down, change the adapter, and then start it up again. So it's not essential, because the thing is that, but I am kind of intrigued by the idea. I'm intrigued by the idea of making it so that the module is hot swappable. Yes. Jackstack said, design decisions also always become technical debt. It is unavoidable. True. Yes. James said, I design in a get out of jail cheaply if you need to change. Scott says, a reset button on the front of the box might be handy when hot swapping DUTs. Maybe. Yeah. I've got to think through that whole reset thing a little bit more. But if, for example, we had IO expanders on the breakout, being able to reset them when they're on the I2C bus could be useful. Ooh. The more I think about it, the more I like the idea of dedicating this pin to being reset, that can be used to control the things on the breakout. But I'm not quite sure whether that should be just connected to a GPIO on the Pi. I don't know. That's a question. All right, so back to wherever we were. So we've got all of our I/O here. So we've got digital I/O, we've got analog inputs, and we've got analog outputs. What else did we have? Oh yeah, here. Okay. This is the least clean part of the schematic, because I was just messing around with this yesterday and it hasn't had any polish put on. Some Call It Fun said, detect a button on the test frame that is depressed when the board is in place to indicate OK to drive all signals. Yeah, you can do that with one of the GPIOs. So I'd thought of that. I've done that before on testers. I've done it so that there is a tact switch mounted on the tester, and when you push the board onto the pogo pins and depress them, it also pushes the switch in, and the tester detects that and it begins the test. So you don't have to do anything, you just push the board in, the test runs. It's really cool. And we can do that now with the existing thing by just connecting a switch to one of those GPIOs and having the tester software detect when that button is pressed. So yeah, we can already do that with this existing system. That's a very handy idea. USB hub. Okay, so I have never used the USB 2046. I've used the 2036, which is the 3-port version of this. It's slightly different. It's got some different I/O pins on it. So what I have done is shamelessly stolen from Austin's Smart Hub project. I had a look at what pins were connected to what. So suspend seems to be an active high connection, so it's pulled to ground to unsuspend the thing. XMEM is active low, it's pulled high to disable, and so on and so forth. So we have the USB connection here. This is it's a vertical USB connector. This is a horrible symbol. I don't know what I was thinking when I made that symbol. I shouldn't have done it that way, but anyway, that's technical debt. A symbol that I did a few years ago in a way that I now seriously dislike. I would not do it this way now. But anyway, I can't be bothered going back to redo the symbol. So it is what it is, and that is the technical debt that I'm living with. So this is the connection from the Raspberry Pi, and that then goes to the input port on the hub, and then the hub has 4 outputs. So 4 ports coming out with their filtration thingamajiggamies on them, and these are going to the breakout. So this is where those 4 USB ports come from. It's from this hub, which is on the board. Now, one thing you can see here is I have not connected the oscillator yet to this, so that as far as I got was this, and then starting to look at the oscillator, and you can see up here I've got a 48 megahertz clock. This is from the TUSB 2036 circuit that I am running on OpenKO, but it looks like the clock circuit on the 46 is different. It uses a 6 megahertz clock or something, and so yeah. So basically what happened here was I copy pasted part of the schematic out of the OpenKO. I deleted the TUSB 2036 and I put in a 46 in its place, and then added the extra USB port, and I hadn't got as far as dealing with the clock side of the circuit. So I think I need to put a 6 megahertz clock in here somewhere. Anyway, I will hopefully figure that out sometime. Yeah. Oh, Don said Xeon has the perfect cobot arm to automate the test board placement. Yeah. Well, actually, we've got an extremely capable robot arm here, which can lift, what is it, a 10 kilo payload with supposedly like point something of a millimeter accuracy within a couple of meters reach. Lachlan has a very expensive US robotics robot arm, and which is the one that he was attaching the chainsaw to. And yeah, it would be huge overkill for this, but it could certainly be used to pick up PCBs and put them onto a tester. Right. James said, with respect to version pins, you could use a fixed number of the GPIO block pins to encode version information at startup. Cable Tie says, and a slight programming error, you get your test board pushed through the back wall of the lab. Okay, now, James brought up a very important point, and Jordan has already responded to it, saying there's an EEPROM of some sort for that info. Yes. So now if I come to here, back to this biggie, the big card edge connector. I refuse to call it a PCI connector now. But I'll slip up and call it that. You can see there are 2 I2C buses right here. there is the bus on the right, which is the Raspberry Pi's normal I2C bus. That is on I/O 2 and 3. So that's what you use for talking to peripherals like I/O expanders, etc. Then there is also a second I2C bus on the left side on I/O 0 and I/O 1. And that is specifically based on the Raspberry Pi hat standard, where an EEPROM is used on the hat to identify it to the Raspberry Pi. So it knows what hats have been installed. It can apply device overlays and load drivers and configure itself, do all of the things. So the contents of that EEPROM tell it what is currently plugged in. So my plan is to put the EEPROM on the breakout module, pass it through the Testomatic board to the Pi. So what the Pi sees is the EEPROM on the test module. So it can identify not just that it has the Testomatic plugged in, but which breakout is installed.
PCI is still suits. Partially correct interconnect, haha.
Partially correct interconnect, yeah. Yeah, so James, your point was insightful, that we should have some way of versioning and detecting what has been plugged in, so that if things do change in future, then we can allow for that. And one of the common ways to do that is with some things like a voltage divider onto an analog input, and you change the value of it and you get a different number coming out, or have a number of I/O pins and you set a number in binary on those I/O pins. All of these options, different things, but for this I'm taking advantage of the support for the EEPROM in the hat standard, so the breakout. I can't believe it's already 12 o'clock. I haven't even got to showing you the assembly yet, but I'm going to get to that. Okay, so this is a partial conversion of that breakout that I was just showing you to use the edge connector. And what you can see down here, this is the EEPROM. Nothing put in the right place or any routing or anything done yet, just slapped on the board. But this is the EEPROM, which is used by the Raspberry Pi hat standard. So that would be programmed with the information that says it's a Testomatic and this is the breakout that is installed, so that the tester can see what breakout is installed and then present that on the user interface and say, we are testing these boards today, and it won't run anything else. You don't have to select what type of board you're testing.
Mitchell R said, at outside the box has converted to Peter.
Yes, Crispian has taken over Peter's job, telling me that I'm about to run out of time. So the idea is that you should be able to plug this breakout into it, and the Raspberry Pi will know what type of board it is going to be testing, because it will read the EEPROM on this, and then it will know. All right, so assembly-wise, one thing that has been annoying me a lot using the existing Testomatic is the touchscreen. It currently has a 5 and a bit inch resistive touch screen. In fact, I've got one, yeah, right here. There are issues with this. So this is what is inside the existing Testomatic. You can see the Raspberry Pi on the back. Attached to the screen, it's plugged into a header that goes directly into the back of the screen. It's got the HDMI loop around connection there, and this is a resistive touchscreen. And I've just found that the resistive touchscreen, well, it's got a couple of limitations. Firstly, the resolution is quite low. I think it's 800 by 480, and that means that when you've got the user interface on the screen, there's really not a lot that you can show. And the resistive touch just is not very nice. It's yeah, I'll click the start button, and I sometimes have to click a couple of times to get it to do it. So yes, capacitive. So this one, what you can see here in my little mock-up, This is a 7-inch 1280 by 600 resolution capacitive touchscreen. And I made a model of it just approximately.
Mitchell R said, we doing capacitive one next week?
Yep. It'll be here by next week. I ordered one from Little Bird Electronics. And not a 24-inch capacitive touchscreen. No. Now where is it? In fact, I can find Elecro. It's actually an Elecro 7-inch.
Scott Miller said, I have a 24 inches capacitive touchscreen here. Maybe an upgrade?
Yep.
Mitchell R said, 2 nice and big physical buttons for the win.
Yeah, 2 nice and big physical buttons. No, not that one. Where is it? Sorry, I'm looking. Oh, here it is. Okay. And this is the screen that I ordered. Right there. So, oh yeah, Andrew said we're not seeing your screen. Yeah, sorry. So this is the screen that I ordered. You can see this thing sticking out the back. That's just a stand. Now, where is a view of the back of it? It's got mounts on the back for... This particular ad doesn't show the back view. Oh, there it does. Okay, so you can see it's got mounts for a Raspberry Pi, and what I'm going to do is use those mounts to attach it onto some laser cut acrylic. And you can see it's got the HDMI and USB connections on the side. Now, keep this picture in your mind. Imagine this display. So this is the 7-inch capacitive touchscreen. This display with these cables coming out the side. And now we're going to switch to this view. And this is the display. So this is a quick little 3D model that I made based on the approximate dimensions of this. So just so I could see how things would fit together. And you can see that because the cables come out of this side of the display, those cables will come out of here and then pass down through this notch, because there's going to be a side on this. Imagine that all of this is in a box. There's going to be a side along here, a side there, on a base obviously, and then the mount in the top for this module to slide in. And with the Pi mounted in the bottom like this, the HDMI cable and the USB cable will plug into the display up here, come down here where the cursor is going, pass through this gap and plug into the Raspberry Pi. So the Pi will sit in the bottom of the enclosure. Then in the back of the enclosure, so imagine that there is a vertical back on it here, there's a power switch and another XT60 connector. So this is a panel mount XT60 connector that will be bolted through the back panel, and there will be a cable that goes from here to the power switch and then into this plug. So the power from the lab power supply will be plugged into the back of the box into this XT60 connector, and that's how the power will all get through to the system. So my plan is also to mount a USB hub in the back. So I'll laser cut a slot in the back panel here, which and then this USB hub can be glued or mounted somehow, clamped down into the enclosure and exposed on the back of the box, so that things can be plugged in, and then this internal cable will just loop around and plug into the Raspberry Pi. That is so that things like the label printer, or if you want to plug in a keyboard and mouse, etc., they can just plug into the back of the tester. Oh, hang on a second, I've just got to close the door here because there's cold air coming in. Tom and Tyra just arrived and and just walked through and then left the door open so I could feel the cold air coming in. Scott is about to say something.
Mitchell R. said, I know someone who can make a USB hub that can be a perfect fit.
Yes.
Scott Miller said, that hub doesn't look like one of Austin's smart hubs.
No, it doesn't. I don't have a model of one of Austin's smart hubs, but that is exactly correct. I just looked for USB hub 3D model, and I just grabbed a step file and shoved it in there. But this could very well be one of Austin's smart hubs. It doesn't actually need to be though, because in this application, this is just for connecting things like the label printer and a keyboard. It's we're not really going to be taking advantage of all of the features of Austin's hub, but it could be Austin's hub mounted in the back there. That would be a very valid way to do this. So
Scott Miller said, measure the one sitting on your shelf.
yes, I've got one. I've got one just over that way. And then you can see the module on the top there. So this shows the general orientation of the parts and how they would fit together. So we've got the new Testomatic mounted vertically. We've got, this has a module plugged into it, and you can see there the EEPROM and all the pogo pins and the laser cut surround for it that puts the device under test in the correct location, and the touchscreen on the front. So yeah, that's my goal. This is the new way of doing it. And then what else did I do? Where I thought I opened another thing. Maybe I didn't. Do I have it here? TM mod test. Here we go. So this is the tester, or the tester squared. I was just messing around with this yesterday because what I'm going to need is a template example or a skeleton of a project for the tester breakouts that can then be used. It can be duplicated and then used to make different variations for different targets. And so I started by doing a board which is a tester for the tester and taking the I/O pins. Fusion did that stupid thing where it lost focus. Yeah, so taking the GPIO pins and bringing them out to LEDs so that they need to be put in the correct position and everything, obviously. So this is like a little breakout that isn't a breakout. All it does is give you LEDs so that we can drive the GPIOs and turn the LEDs on and off, and I'll loop back the DAC outputs to ADC inputs and that sort of thing. But it means that we can plug this in and we can test all of the I/O on the tester. Put a Pico PD trigger board in it. Okay. That sounds like something I should look into. Back to here. The Testomatic tester. Yeah, so this is like a minimal plug-in breakout that doesn't have any pogo pins. You just plug it in.
Peter Lawler said, duh.
Yes,
Outside the box said, is that your tummy rumbling?
Yes, it was. You could hear that. Yeah, so you plug this into the Testomatic, and then the Testomatic can drive all LEDs and do stuff, just to verify that the Testomatic is working. And then this could be used as a template later. So if you wanted to make your own version of a test breakout, you could start with this, and it's got all of the pins and things.
Said, dislike and unsubscribe.
Yeah, it's got all of the pins here, and you can see the symbol is the same. So what I've got is one part with two footprint variations. One of them is the edge connector that's on the Testomatic, and the other is the PCB edge that is on this. So it looks exactly the same in the schematic, but it's different physically. One is the PCB thing, the other is the socket. So what you can do is, if you wanted to make your own breakout, you would start with this schematic and you would just hook up all of your test points to the I/O here in whatever way you see fit. So that's and it's got the ID EEPROM down there. Oh, that is not assigned. IO1 EEPROM SDA. That should be IO0 EEPROM.
Peter Lawler said, need
SDA.
a tester for the tester.
Yeah, that's right. We do need a tester for the tester. So that should be, come on, name that. That should be IO0, no, IO0 EEPROM SDA. Yes, yes, that's what I wanted to do. Testomatic module test, TM mod test.
Peter Lawler said, bye.
Bye, Peter. And I think that's kind of it. That was a lot. That was a lot. Once, as usual, I don't understand how it took me more than 2 hours to just describe a few things. But I have a knack for describing things in a very long-winded way. So this is where I'm up to with the Testomatic. And where is it? Testomatic assembly. Yeah. One thing that I brushed over is the infrared camera connection. Oh, this assembly is out of date. Hang on. Let's update it.
Cable Tie said, this is looking really good, John.
Ah, thanks, Cable Tie. There we go, that's better. So now it's got the external button connector, it's got the IR camera connector. Oh, that's right, and the so extra USB ports. Another one would be for something like a webcam, like a USB camera, that would be mounted above the tester looking down onto it, so that the tester could take photos of the board that's being tested for record purposes, record keeping purposes.
Scott Miller said, tester for the tester next.
Yeah, testerception. And the IR camera, this is for a specific IR camera module which I've ordered, and it's a very cheap little IR camera that provides a couple of outputs. One of the outputs is a serial connection where it dumps data for each of the pixels. Basically, it's like a...
Box said, it is good you got all this done while being unwell, but I wouldn't recommend it as a regular strategy.
Yeah, that's right. It is not a good strategy. It's basically the way I get some peace, is to get sick. So the IR camera dumps out a frame of data in text format, essentially. It's a series of numbers, and the numbers... ooh, interesting idea, Andrew. Yeah, Andrew said, what about bringing these LEDs up to the edge of the board for more visibility? That could be a good idea. I could even make them edge mount LEDs so they shine up. Ideally, they'd be on this side of the PCB, but yeah, they don't really need to be there. Maybe what I could do is, what would be more useful would be having LEDs on the breakout, because then they would be visible right up here. So I think I might do that. So having these LEDs on here shows what the tester is trying to drive, but I could also put power LEDs on the breakout depending on which ones are being used.
Cable Tie said, or maybe light pipe able.
Yeah, light
Austin's
pipeable.
_creation said, use fiber optic cable to make the LEDs shine elsewhere.
You both had the same idea. The screen would be in the way of having them on the opposite side, says Andrew. Yes, that's right. So I don't think they're going to be super visible either way if they're on this PCB. They would need... So I think it's okay having them down here. These are really for diagnostic purposes. If I wanted them visible, I'd stick them on the right, on the breakout. So an LED could just go on the breakout right here. It's got those same power rails come through to here. They are right there on these connections on the top of the PCB. Oh, Jordan said, if you got rid of the LEDs, you have room for a longer card-edge connector for future expansion. Yeah, I don't know though. I think I've covered myself. There are a lot of connections there already. There are 124 pins. And at a certain point, you just have to say anything else in future, we don't know. I think I've covered it enough. We've got 24 digital I/O. We've got 16 analog inputs, 16 analog outputs, I2C, SPI, 4 USB ports, and 3 controllable power rails, all being brought up to this tester breakout. So if that isn't enough to do what we want to do, then, well, we're kind of screwed. So, yeah. Is it worth adding, Jeff asked, is it worth adding another I2C device on the tester to test the second I2C? Maybe. That is a good point. I hadn't really thought of the tester as being, yeah, anyway. Yeah, that is an interesting point though, Jeff. Yeah. So, what am I doing? Okay, I'm going to close that. Don't save. Don't save. That's right, I was talking about this IR camera. I keep trying to talk about this IR camera. It's a little camera module. I'm going to see if I can find it. And then I'm going to have to go because I'm going to have to contact this client back about coming over this afternoon. Where are we? Camera module. This is the module that I have bought. It comes in 2 different versions, which has got different focal length, different lens with it. And I've never used this before. It's a 32 by 24 pixel IR camera, which is fairly low resolution, but I think it's adequate because we don't really need super high resolution here. We just want to see if there are any major hotspots on the board, like if motor drivers are overheating or something. So I think that resolution is okay. It's $52, and it has an I2C interface, and it also has a UART interface. And from what I can tell of the way these work, oh, excuse me, is they dump out. Where are we? Oh yeah, so this the serial port directly outputs 768 temperature data, and USB turns TTL directly to the computer to see the data. Yeah, so what that is saying is, so what's the resolution here? 32 times 24 is 768, I believe. 32 times 24 equals, yeah, 768. So what happens is that on the serial port, it dumps out a chunk of data, which is 768 values corresponding to all of those pixels. So it's just like a raw text dump of the of a frame of what it can see of all of the thermal values. And I found example code dealing with this using Pygame to generate a thermal image, and yeah, so to parse that data, to take the 768 values and generate a PNG or something using Pygame. So we can use this data and either save the data just as a raw chunk of text, like we could save that against the test record. And one of the interesting things is because it comes in as a chunk of text, it means that we can process it. We can actually parse that data in the tester to do things like see what the maximum value is in the array coming back, so we can see the the highest temperature that is being read by the camera by just parsing it in Python, which makes it very easy. And we can also generate an image out of that raw data and save that image on disk as a PNG or whatever format we want. So I think this is, I went around and looked at a whole lot of IR cameras, and most of them are in the $300-400 region. And this seems like a very small, simple and economical way of getting IR data that we can then process. So this camera specifically, which one was it? The BA? Oh, the BAB. This is the variant that I ordered is the BAB, which has got, you can see that lens is quite long compared to this one, the BAA. It's got a shorter lens. The BAB has a narrower field of view, which means it can be higher above the test board and still get the whole board in. I didn't want to have the camera really close to the board. So the connections on here, you can see V in, ground, RX, TX. That should be all the connections that we need to the camera to be able to get its data back
Outside
over
the box
UART.
set. Hi from Jane.
Oh, hi. Hello, Jane. That's Crispian's mum. So that is why this header is on here. This is all a bit of an experiment. I don't have one of these cameras yet. I ordered one. It hasn't arrived yet. I only ordered it a couple of days ago. And the idea is that we should be able to pull the data off that camera and read that with the Raspberry Pi. Oops, rendering has gone nuts. All right, so if I plug that camera into here on the header, that connects through to a UART on the Raspberry Pi. All right, one final thing. One thing that I did not explain at all is how the Raspberry Pi connects to this. And the short answer is IDC cable. So a 40-way IDC cable plugs in there and then would just loop around and plug in there. So the Raspberry Pi can be mounted in the bottom of the enclosure on some standoffs, and the IDC cable will just loop over and connect it. Now, the way this is oriented, it also allows another option, which is either the Raspberry Pi could sit there with an IDC cable connected, or it could be rotated 90 degrees.
Mitchell R said, you can probs make an image from it and store that per board for historic info reference.
That's exactly my plan, Mitchell. Yes. There is a whole other side to this, which is the storing and reporting of the test records. That is a big kettle of fish, and that is a thing that we will get into in the future with Mitch, because Mitch has been working on all of the magic that is part of that side of it. But we're not ready to reveal all of that yet. But that is super cool, really super cool. This, now if I, let's see, if I go to, where are we, Raspberry Pi, and then I move that, so this, 90 degrees, and then move it here, and then move it up, which way, move it, about there somewhere, a little bit more, not so much, there. Well, it's not quite aligned, but you get the idea. You can see that I will move it up a little bit more to improve that alignment. 30, probably 23 millimeters. That looks about right. Close enough. All right, so what you could do, instead of putting the pin headers on the top of the Testomatic board,
said, should listen to Opulo.io podcast. They talk about their testing and saving data process at some point.
Oh yeah, I've listened to that. No, they don't go anywhere near far enough. No, wait until you see what we're doing with this testing system from the software side. It's pretty incredible. So the yeah, I know Lucian is kind of obsessive with process and that sort of thing. I'm sure you can hear the bikes going past. This is what happens when you're right around the corner from a bikie clubhouse. So instead of putting the pin headers on the top, you could just put a socket on the bottom and plug the Raspberry Pi in, and essentially this is like a hat. So Testomatic you can think of as being like a Raspberry Pi hat. It's just in a strange shape, and it is not normally mounted, and it's not intended to be mounted directly on top of the Pi, but it could be. I mean, this thing could be mounted like this if you had a different idea about how to connect all of this up. And if
Austin's
these cables...
creation said, bikes saying lunchtime.
Yep. So these, and in fact this may well be a legitimate way to do it, instead of mounting it in the bottom and run the cables through into here instead. It's just that I think by putting it in the bottom, it'll be a little bit easy. It won't be as all jammed up and as tight. But yeah, that would be a legitimate way to mount it. So I'm just going to undo that and move it back to there. And I'm going to pull that, re-pull the update, and then I'm going to go, yeah, there we go. So this is the approximate layout. Imagine this in a box, but the box is invisible. So yeah, back face there with these mounted in it, sides on it, a base, like a triangular shaped, so the side would come along here and then come down at an angle. It's a 45-degree angle, so it'd be like a triangular shape to the side there, and a piece of laser cut acrylic that is lying at a 45-degree angle with the screen attached to it. So the screen has those mounting bolts on the mounting holes on the back for attaching the Pi. My plan is to use those mounting holes to attach the screen through the acrylic, so it'll be attached on the front of the box. So I think it's going to end up looking really cool.
When I say PCI slot, just the pins on the board. Scott Miller said, hell of a lot easier to cool in the bottom.
Yeah, that's true. A lot easier to cool and a lot easier to access. Because the thing is that when this module is removed, like when that's unplugged and slid back out of and removed, the whole top of the tester box is going to be open. So it'll be possible to stick your hand in and get access to the Raspberry Pi and all of this stuff that's underneath. So easy for maintenance. Maintenance of the tester. Okay. I think that's probably enough for today. What do you think? Are we done for the day? Need a handle on a test board. Right. Okay, Any Mule's made a good point. Need a handle on the test board, as pulling it out of the slot will need some force. Yes, okay, so my plan with that is, so this is not the final shape of the tester module, because it needs to be able to sit into a little ridges to hold it. It's not going to be just flapping in the breeze, hanging off the PCI slot. It'll be sitting...
Mitchell R said, hit that like button, peoples.
James asked, are there zero insertion force PCI slots? That would be nice. If there were, I would use one for sure. I've never seen one though. Yeah, so there will actually be like a little ridge along here that this sits in, so it'll be mechanically supported. And then I was thinking of having the back come out with maybe a couple of loops on it with holes in it, so that you could put your finger in and pull it. So you've got good mechanical handles on the back here that you can grab to pull the module out and disengage it from the card edge connector. So imagine instead of just being like a rectangular block like this is now, it'll actually have one of these layers coming out further, like sticking out 5 millimeters from the side, so that it can be supported on the tester frame. And on the back, it'll have a couple of tabs coming out with laser cut holes in them so that you can grab it and pull it, or maybe just a tab in the middle, something like that. Like imagine a rectangle sticking out the back there as a handle for removing it. And also, you may not have noticed, I mechanically mounted the PCB right here adjacent to the slot, the card edge connector. So it's got mounts in the corners for the PCB, and then it's got an extra pair of M3 bolts that will go directly beside the ends of the connector. And then this will be, so that will be bolted through that hole, and then with a little standoff, and then through a sheet of acrylic. So there'll be a vertical piece of acrylic here that this will be bolted to. And because I've put these really close to the ends of the connector so that it will take the force, and you can see that there are the connector body here pushes against the PCB. So when the card is being inserted, the force of being inserted into that slot will transfer through the PCB and through these mounting bolts. And when you pull the module out, it'll pull out of this slot, and once again the PCB will be very firmly supported directly adjacent to the card edge connector. So I think this should end up being very strong and rigid. And you can see there'll be 4 mounting bolts on the top edge here, and then 2 at the bottom. So keep those ideas coming, folks. Any Mules asked, earlier I asked about ergonomics of changing the boards too. Would swapping from the side be better than from the back? I don't think so. I did think about this. I thought about having like a side mount module, but I think from the back is the logical way to do it. Yes. Austin asked, in the case of INA chips and drift LEDs...
Scott Miller said, seems more rugged than a computer motherboard implementation.
Yeah, I think so. Yeah, putting PCI cards into computer motherboard, sometimes the motherboard can deflect quite a lot. However, there is a thing here. When you are putting a PCI card into a motherboard, typically what you'll do is put it down a little bit asymmetrical, like get one end in and then sort of twist it and push it as you push it in. And we can't do that with this. It has to be directly aligned and slide straight in. So you have to overcome the force all the way along simultaneously because of the restriction of the module sliding in on its little mounting edges. So it's going to come in and engage directly into the card and be mechanically constrained. So it'll be forced to engage with the card by coming straight in on it, into it, instead of coming in at an angle and being able to sort of wriggle it into position. Scott says, twist-in method is a major cause of motherboard failures. Yeah. Yeah, it's not mechanically good, but that's the reality of how people do it. So this is forcing the board to go straight into the connector with no rotation whatsoever. Cable tie, see you next time.
Cable tie said, I have to run, peeps. See you next time.
Gerald said there is a ZIF adapter from eTesters. That's interesting. That is interesting. I'm going to have to look that up. But I am tired and I'm going to have to stop. It's 12:35. What is going on? How did you allow me to overshoot the time this much? It's your fault. James Harris said, Eurocard chassis have little levers to provide even force. Right. Cool. Some call it fun said, there's always V2. This is V2. V1 was Testomatic. Was the Testomator. V2 is the Testomatic. This is the new reimagined version, but it is definitely V2. So, yeah, by next week, I will have, what will I have? I'll have the touchscreen. I should have the IR camera, I think. I won't have PCBs yet because I haven't even finished doing the routing on the PCB and I still need to make a few more changes.
Scott Miller said, fault? You think it's a fault?
So next week we will not have an assembled thing, but we'll have some of the parts at least. My guess, so I think maybe next week, the thing to do is next week will not be about Testomatic because it's time to talk about something else. And I won't have the boards back yet. But by next week, the boards should be in production at least. And then the following week, I should have the actual PCBs and I'll have the touchscreen and everything else. So by 2 weeks from now, so not this live stream coming up, but the next one, I should have a moderately complete Testomatic that we can play around with. Yes. Oh, Jordan said, I'll be very curious to see that IR camera. Yes. Yes, I will be as well. I do have an IR camera. Where is it? Oh, it's out near the tester. But it's a higher resolution than that one that I was just showing you. But the driver software for it is kind of weird and it's also moderately expensive. I think it's like a $300 camera. So being able to do 32 by 24 resolution IR for 50-ish bucks.
Austins_creation said, lunchtime.
Is really appealing to me. And if it works as well as it looks like it should, then yeah, having 50-ish dollar IR cameras with a UART interface is a good thing. Yeah. Right. KHT wants to know, what are we going to talk about next week? I have no idea. But anyway, in any case, I am going to go now and don't know, but I'm going to go. I need to eat, get my energy back, and I will talk to you all on Discord. If you jump on Discord, people. I know I'm not there very often. I want to be there more often than I am. But
Outside the box said, Guru there.
I'm trying to make a conscious decision to get onto Discord more often and show progress of things, like post pictures of stuff like this that I'm working on. And I've had some really good feedback in Discord. A lot of the changes and rethinking that I've done around this is based on ideas that people have given me in Discord and in chat on the live streams. So come along, join Discord, and the link is superhouse.tv/Discord. There's an open invitation there, and we'll talk to you, we'll chat. So, yes. Okay. Mike, you came along as well. Thanks, everybody. I hope you have a fantastic week, and hopefully by next week I will no longer be sounding like I am on death's door and coughing and sneezing. So I will do the things. You go and do the things. Have a fantastic week, and thank you very much. Hooroo.